Thank you, Mike. Let's give Mike a round of applause, please.
Thank you, Tony. I appreciate this very much, and I'd like to say from NanoRacks, we're very excited to participate in this offering. We'd like to thank the Space Florida folks. They put a ton of work into this, and Mr. DeBello and Tony and the team have just done a fantastic job to get the system up and running. I'd also like to thank our friends at CASIS for their continued support and backup in our efforts at NanoRacks. And of course, I see some NASA faces in the audience too, some good friends, old friends. And we've been in business for about 3 years now. It's been a fast and exciting ride, and for those proposers here who may win this first round, and hopefully there'll be other rounds that we offer together. You'll find that it's a very fast ride. You're going to do a lot of work, a lot of hard work, but at the end of the day, we're quite sure you'll get a lot of satisfaction out of the process, and it's really fun. Another thing I'd like to mention too before I begin, I get a lot of people that come up to me and say, well, gosh, how is it possible that you could start a small company like this at this time when the space program is over? I said, well, wait a second, what do you mean the space program is over? Well, the shuttle doesn't fly anymore. Well, we were able to fly on 2 shuttle flights, the last 2 shuttle flights, and I have to say that I've been in the commercial space business for about 22 years now, something like that, give or take, and I've never been busier in my life. Because of the space station, the International Space Station, and the visiting vehicles that go to the International Space Station, we're now seeing something we've never seen before. We're seeing, well, I like to brag at the company that we fly every quarter to the International Space Station. That's not true. We actually fly upwards of 8 times a year to the International Space Station. There are many, many flight opportunities. We have of course, the SpaceX Dragon is now flying. Also, another bragging right that Rich didn't get to talk about earlier, we were the only payload on the SpaceX demo flight. We flew actually a 2U box, is twice as long as this, with some high school student mix sticks on them, little chemical and biological experiments. And we flew out to the International Space Station on the SpaceX demo mission. We were the only payload on there because the rest of the cargo was basically inert cargo. Some people were concerned that it wouldn't make it to the space station. We had faith in this vehicle, and man, it works. It's a fantastic deal. So, of course, and in fact, just yesterday we delivered another set of payloads that will be flying up on SpaceX 1. So, as far as frequency, we have the SpaceX Dragon, we have the Russian Progress vehicles. We've flown on Russian Soyuz up and down. We have the European ATV vehicle, the Japanese HTV vehicle, and very soon we'll also have the orbital Cygnus vehicle. So when you combine all this traffic that's going to the International Space Station, we have a lot of capacity to fly things, and that's why right now is probably, I have to say, it's one of the most exciting times in the space program that I've ever seen, and I've been in this business for about 23 years now, and it's just a great time to fly. So don't ever let anybody say that the space program is over. We're just at the front end of a really exciting time. So I'll get on with the presentation here. Welcome to NanoRacks. We started NanoRacks to create a commercial environment for economical space utilization. There are a couple of factors associated with economical space utilization. One, of course, is money, so that's easy. But the other is time. In a lot of cases in the past, I used to see in my experience in the commercial program that it took a long time to get payloads from the inception phase to the flight phase. A lot of times I'd see graduate students in universities actually having to abandon their projects because it took too long to get things into space. So at NanoRacks, what we've tried to do is we try to boil this down to a 9-month cycle. This is what we advertise as basically from the point where you sign up with your program, which in this case would be you'd win this solicitation. And as Tony mentioned earlier, it's a very fast process. We'll get you manifested, get you into the system, particularly in the safety system on the NASA side, help you build up your payload, get it ready for flight, and get it ready for flight, deliver the payload, and get it on orbit within 9 months. I say 9 months, sometimes I'm lying. Usually it's about 6 months it takes to get that on board. So we can do this very quickly, but we do require that you participate in that too, and sometimes it's kind of a give or take situation. So, but like I said, it'll be a fun ride. So we also feel it's vital for America to have a cost-efficient means to utilize the space environment, and we're also getting a lot of backup from NASA cases, Space Florida, everybody. We're all, I think, on the same page where we really need to utilize this fantastic asset that we have on orbit called the International Space Station. And in fact, at NanoRacks, we're seeing worldwide participation too. All countries. In fact, the CubeSat that Rich just showed earlier in his presentation was from Vietnam. We had a lot of eyebrows raised when we flew that satellite, but it was it was exciting. I'll leave it at that. So at NanoRacks, we try to utilize plug and play as much as possible, miniaturization, standardization, and commercial practices to meet these space environment challenges. Another point I want to make before I go on, the microcontrollers that you'll see later, what Steve Bress is going to talk about from Celestial Circuits. Every once in a while I have to step back and pinch myself, because when I started in the space program 22 years ago, these things were not available. In fact, we didn't have email, okay? For those of us in the room that remember when there was no email, no internet, wow. Now all of a sudden, look what we have. In particular, the microcontrollers. And I'm going to steal a little bit of your thunder, Steve. But this board here is more powerful than the computers I use to help send shuttles into space. In fact, this is more powerful than some of the early shuttle computers, and it's definitely more powerful than what we went to the moon with. And this fits, on the palm of my hand, and interfaces with computers on board right now, and it's a fantastic thing. The microcontroller has become pervasive in our society. It's in your automobiles. You drove in with one this morning. You have them in your cell phones. There's probably one in this mouse. Okay, so they're everywhere. They're cheap. They're easy, and they're super powerful. And you can do some fantastic things with your experiments with these microcontroller boards. So we'll go to the next slide. So a typical NanoRacks mission to space will start by launch on some vehicle. As I said, there are about 5 or 6 choices that we can launch to the space station. In this case, this is the Japanese HTV-2. HTV-2 delivered one of our experiments here. It's seen berthing to the International Space Station. Commander Kelly over here is working with some of our mixed sticks. This is one of our passive experiments that we flew earlier. And it happened to return on Soyuz 24. Landed in the middle of a snowfield. That was kind of cool. They pulled the crew out, pulled our experiments out, and about 14 hours later, I was receiving them in the laboratory in Houston, where our main facilities are. On every single Soyuz flight, there is at least one American astronaut coming home. That means that there's an aircraft in Russia that's picking up that American astronaut and our payloads, bringing them back to Ellington Field in Houston, Texas. And we received these payloads. These came back so quickly, they were still cold and they still had snow ice on them from the pickup. That was really cool. So this is a typical full mission. In some cases, you may remain on orbit, and if you have the appropriate instrumentation, you can downlink the results of your experiment and actually see real time or near real time the results of your experiment from the ISS. In those cases, typically we don't bring the payloads back because there is, as you can imagine, limited space in the Soyuz vehicles right now. It gets a lot better though with the Dragon capsule. Dragon capsule is much larger and we'll be able to do more of that. But the return frequency of the vehicles is something on the order of maybe three times a year minimum. So it's a lot less than the actual ascent situation. So, getting to the heart of the matter, most of the NanoRacks facilities are located in the Japanese experiment module. And it's located over here on this side of the space station. Most of the U.S. vehicles are berthing to this node down here, I believe, and then a lot of the other vehicles, the visiting vehicles, are docking to the aft end of the Russian service module, which is on this side of the space station. So, and as you may know, the space station continues in this orientation. So this is interesting, say, for a lot of the radiation researchers. The space station is flying in what's called an LVLH, approximately LVLH attitude, where the top of the space station is always pointing away from the center of the Earth, and the bottom of the space station is always pointing at the center of the Earth, and it continues to rotate around like that. Whereas the solar panels on the outside rotate on these special gimbals, and they track the sun. So if you're sitting on the space station, you look outside, you see these solar panels are kind of rolling around, tracking the sun. Kind of gives you an idea of where we are on the space station. So once we're inside the Japanese experiment module, the NanoRacks, NanoRacks has 2 lockers that hold our frames 1 and 2. These are our original facilities that we sent up on 19A and ULF-4 back in, let's see, it was March, April time frame of 2010. So we have these 2 facilities on board, and we'll get into this in a moment. But these fit into what's called an express rack. Express rack holds a total of 8 mid-deck lockers, and that's what this little box is here. It's got a door that flips out, and our frame slides into this locker. And inside the locker, we can fit up to 16 of our NanoLab cubes. So 16 of these cubes at one time will fit into a NanoRacks frame. The frame provides power and data connectivity to a patch panel in the front. We'll go to the next slide. So here you can see a little closer view. We have a patch panel on the front that has 16 locations where an astronaut will take an express rack laptop. It's just like a laptop computer. And you can plug into any one of these 16 locations and it will address your USB device, your cube basically, that's on the inside of the frame. As you can see, when the locker is closed, we take out the center panel of the locker and you have access to that front panel. So once everything is slid in, we can access the data port of your experiment if your experiment is designed in this fashion. We also have a power connector here that goes express rack power and a little circuit breaker switch. We provide a continuous 5-volt USB quality power, which is 5 volts at about 2 watts of power to each of the 16 locations on the inside of the frame. Now, just because we put the frame inside the locker and button it up, that doesn't mean that it's not accessible by crew. A lot of times we'll fly passive payloads that are actually stored in these mid-deck lockers where crew members can come up, they just pop open the door, pull out your experiment. For instance, the mix sticks that we're flying, they operate like a light stick, where they have 2 or 3 chemicals inside, where we have the crew members just break the inner ampule and mix the chemicals. We also have some other experiments I've been talking to some folks about where Rich had mentioned we have a plate reader on orbit. A plate reader, for those in the laboratory field who are familiar with it, it's a spectrophotometer, so it shines light through a standardized sample tray. In the sample tray, I think this could also be done in the solicitation. You can arrange to have a sample tray with certain, say, biological, or in some cases there's some radiation detection chemicals that we would fly up on this plate. They'd be processed for a period and then taken out by the crew and put into the plate reader and read. So crew interaction is possible, and I like to encourage automation as much as possible, though, because the automation is a little better guarantee that you're going to get your experiment performed in proper and timely fashion too. Sometimes the crew time can be usurped by other, say, emergencies or situations that happen on the space station where, for instance, this last couple of weeks we had a lot of EVA work that had to go on. Crew had to repair some things, and it chopped up a lot of the science time that the crew had to perform experiment work. So in this case, if your experiment is automated and running, say, off the microcontroller with just simple commands, you can definitely guarantee, you have a better guarantee that your experiment will run in a timely fashion. So getting a little more detail, you can see here on the left-hand side, you have the frame without the cubes on it, and over here you have the frame with the modules on it. Once again, too, the interface between the cube for the NanoLab and the NanoRacks frame is through a USB Type B connector. You can have a female Type B connector. This is the same kind of connector you see they use on printers typically for computers. So Type A connector is that kind of flat, wide USB connector that's pretty popular, especially on a computer like a USB stick. The Type B is the printer side, and that's what we use on the inside of the frame to connect the cubes to the frame. A lot of people ask me, is that all you use to hold the frame on, or hold that cube on in orbit? I said, yeah, because it's microgravity, these things aren't hanging, so when we play with it in 1G, you know, the cubes are kind of hanging, it looks really weak, but in microgravity it's no problem. So another interesting point about the way the NanoRacks frame and locker and express rack work is the system uses what's called a rear breathing thermal control system. So we have an air inlet in the back, and if I go back one slide, you see here's the air inlet side and here's the air exhaust side. It's kind of a mesh filter on either side to collect any debris that might form, and usually what you just see is fuzz. You know, it's like in your house. The filters in your air conditioning unit just gets a little fuzz on there. And so what we have is we have cooling air that comes in from the express rack, is circulated by a little fan that's in the central unit here, and then blown out the back. And this is how we kind of keep a moderate temperature and cooling temperature inside the box. And typically the inside temperature, that's kind of important for a lot of the biological experimenters, it's typically about 80 degrees Fahrenheit. They keep the space station at about 80 degrees Fahrenheit because there's always air blowing around, because of microgravity. If you don't have air circulating, carbon dioxide that comes out of your mouth tends to pool around your head. So they want to keep the astronauts supplied with fresh oxygen. They keep the air circulating. But if you have a fan blowing on, you get a little cold. The humidity is a little bit lower, a lot less than it is here in Florida and Houston. And so the crew gets kind of cold, so they raise the temperature up to about 80 F. Okay, so getting down to the nuts and bolts of the situation. This is a NanoLab kit overview. This slide's a little bit older. The end plates look a little bit different than this, but basically we have a central aluminum box with injection molded end caps, look like this, right? And inside we have the Entropy Engineering Celestial Circuits circuit board, which has a microcontroller and a USB port on it. One other thing too, I'm still a little bit more of Steve's thunder. This microcontroller board that he has also has programmable FPGAs on it, which is another amazing thing that didn't exist 20 years ago. It's a cool little thing. It's basically a programmable electronic circuit where you can program the circuit on the fly to do physical electronic parts. It's a fascinating chip, and I wish I had more time to play with these things, but you can do some amazing things with this system. So it's a very powerful board. So bottom line is, we supply, or this solicitation through Space Florida will supply this kit to you but it's up to you to put this experiment in here. Now, a lot of times, when I work with students, I get the blank look. What I mean by this is we've all suffered this problem where you do your exam and you get your little blue book, right? And you have to write an essay, and you open up that blue book and it's blank. So what do I put in here? What in the world do I put in here? Well, this is where I'm leaning on your creativity. Those of you who are going to propose on this solicitation, I'm expecting some very creative things to come up. And I've seen some really cool things come in over the 3 years that we've been doing this stuff. So I have faith in our youth. I have faith in our researchers too, to come up with some really clever ideas to put inside the box. Another thing I wanted to stress too is at NanoRacks we really lean on open source. So we're very fond of the open source situation. We provide everything openly to our researchers. And as far as intellectual property is concerned, that's your problem. If you have something you want to patent or protect that's inside the box, we respect that, and we will support you in any way we can in that regard. And we don't want any rights to your stuff, so we'll always keep that separate. So, now we'll get into what do we put inside the box. So, I believe in this solicitation that we are offering at least a 1U, just a 1U cube, okay? And I think it may be flexible. We probably have to address it as the situation comes up. But in some cases, I found a lot of experimenters need a little bit more room than a 1U cube. And in fact, just by keeping to this 1U format, we can actually go out maybe another 5 centimeters on one edge, say in this direction. And usually I find people need that for cameras that they put inside. We've found a lot of USB cameras that have been run by the microcontroller boards to look at things in experiments, particular plant growth experiments. And sometimes we need a little more focal length. If we go back a couple of, let me use this slide here. We can grow about 5 centimeters in this direction away from the plane of the NanoRacks frame. So it gives us a little bit of flexibility in that direction. And a lot of people use that instead of going in this direction, because if you go in this direction, you're actually going to take up like more than 1U of volume. And that typically sets you into getting charged for 2U. 2 or 3U. But just for future reference, we can have payloads of any of these sizes that will fit into the NanoRacks frame. And the other interesting advantage, when you go to these larger units, you can actually pull power from more than one of the USB Type B connectors. So it's in increments of 2 watts that you can increase your power input into your payload. So you can get up to 16 watts, 8 times 2 watts, or 16 watts of power in something like this. So mass-wise, we generally try to stick to 1U equals 1 kilogram. That's not critical though. Another advantage of this flying with the internal pressurized cargo, weight is not as critical as you would see, say, if you're building a CubeSat as a secondary launcher. Those guys are very tight on weight restrictions. They're always trying to minimize weight as much as possible. In our case, with flying inside a pressurized volume, there's typically an allocation, and typically that allocation of mass is volume limited. So it's a very interesting situation that these pressurized vehicles typically fly lighter than what they're expected. So if you can make a little more dense payload, if that helps you to make a denser payload, we're okay with that. So mass is not as huge an issue as one might think. Power-wise, we are restricted to 5 volt DC at 400 milliamp. That's just USB standard. So if you can power your USB device off of your laptop, That's always my litmus test. If you can run it off your laptop as you're working with it on the ground, you're in good shape. USB 2.0. We are not going to 3.0 yet. So once again, each one U cube has a USB Type B female connector, 5 volts, 400 milliamps, and USB data connectivity. The collected data is transferred to a laptop computer in near real time, which this means it's kind of like SneakerNet a little bit, where the crew will, at some designated time, and typically we can do a maximum of 3 data takes during a week. Here's another kind of secret to operating on the space station. The crew on the space station operates a 5-workday week, Monday through Friday, on, I believe it's UTC Standard Time. So it's almost Moscow time, but not quite. Used to be Moscow time, I think. So they operate kind of, for us in the States, it's kind of a weird time. We usually have to get up very early in the morning to see some of this stuff. So that's a future warning. Don't get too much sleep, right? The second thing, though, is they have weekends off. So they don't operate during the weekends, and they operate an 8-hour workday typically. So usually what we'll do, as far as maximum data takes go off of our payloads, we'll do a Monday, Wednesday, Friday data take sequence. So if you start thinking about how you would operate your payload, in particular if you're taking photographs or video on the inside of your payload, you have to kind of watch your data management in that regard. So you would size your data collection system. And typically people just use SD cards for this stuff. It's another miracle that's occurred lately. An SD card with 64 gigabytes of memory. I would have fallen over dead if you would have told me that in 1991 that was possible. It's amazing what's available right now. So if you size your data collection system so it can handle this operational mode of data dumps, say 3 times a week, every other day, and then weekends off. That's another good design point. We can also send up commanding files. I don't like to say the word commanding. NASA doesn't like that, but we can send up, say, protocol files that can be transferred from the ground up to the payload via the laptop. So if you're finding that, say, during the course of your experiment, we're downlinking some data and something doesn't seem to be going right, you need to change some parameters, we can uplink a data file from the ground, and actually from the convenience of your armchair, now that we have internet, right? We can uplink this file and you can change or reprogram your microcontroller to change your experiment sequencing or any other parameters you may want to change, say heater temperature, or fan speed, etc. Many things that you can control. So, here's the meat of the topic, okay? What do we want to put inside of the box? Now, I don't want to guide anybody in here. I have some personal experiments that I'd love to fly. I haven't had a chance to, so maybe I'll throw out some suggestions and some of y'all can maybe fly these experiments. I'd like to see that. I just don't have time to fly them right now. But starting from this side, we'll talk about space research areas. In microgravity, of course, the really cool thing that we get to see by flying on the space station is basically we're giving you at least 30 days of microgravity. Now this is something that even in the shuttle days, you know, the best we could do is about a little over 2 weeks on the shuttle. And so there was this whole set of science. I ran into this when we first started NanoRacks. There was a whole set of science that was designed to fly in 2 weeks. That was it. I'd say, but guys, I can give you 30 days. And I'd say, I don't need 30 days. I need 2 weeks. Well, I can't bring you back in 2 weeks. Well, I can't do my science. It's like, no. Reshape your mind. Reshape your mind. You have 30 days or better to fly this science. If you only need 2 weeks, design your experiment so that you can see your results over those 2 weeks or within those 2 weeks and downlink the data. Typically, we end up where we're actually flying more like 2 months or 3 months before we can actually return stuff even, because of the frequency of the Soyuz return right now, or the Dragon return. It's typically on the order minimum about 2 months, or it really depends on how we time the flight. So there's a little bit of, we'll need some flexibility from the experimenter side in that regard. But as far as long-term microgravity, y'all are in a sweet spot right now. This is the first time in history where we've really had this kind of access to long-term microgravity. And we've seen some, already in some of our early work, we've seen some really cool stuff come out of this, where people were getting unexpected results from long-term microgravity. In particular, I'm very interested, there's some protein crystal work that's going on. CASIS has got some programs that are being sponsored, and there's some fantastic things that are coming up where we're going to have the opportunity to grow crystals on the station for periods that we've never had before. There's also some long-term, just regular, non-biological crystal growth. In fact, we've had some of our student experiments. We flew an electroplating experiment. And I searched the archives. I wasn't aware of any other electroplating that had ever been done, at least intentionally, on orbit. And so we just returned that experiment, and I'm hoping to see some really cool things there. I'm expecting to see some different crystalline structure size with that. So, any kind of electroplating, electroforming, electrowinning experiments will be a fantastic area that's just literally untouched right now. So let's go down the list a little bit. So fluid science, fluid handling. There's been a lot of things in the past on this. The nice part about the fluid experiments are usually very quick. They happen quickly. These are also very good candidates for the suborbital flights and things like this, because these experiments happen very quickly. But there are certain instances where, maybe long-term settling of fluids or long-term fluid dynamics, you see vibration of the fluids operating over time. You have this very large time constant that you can deal with now on the space station. So you can see some fascinating things with that, especially capillary flow too. Capillary flow or any kind of fluid transfer work. This is all going to be critical. The other thing I want to mention, your science, if it's applicable to going beyond Earth orbit. For instance, experiments where you see propellant transfer or things that could help future vehicles are going beyond Earth orbit. These are all very interesting. There are a lot of people who are very interested in this, particularly at NASA right now. To see new technologies and new things being brought up in this area. Soil mechanics science. A few years ago, 15 years ago, there were some fascinating experiments that were coming out of Marshall. I believe it was called MGM, where they were looking at soil mechanics without gravity. Soil mechanic or soil engineering, say flow of sand, flow of mud, flow of earth, earth materials, is always under gravity. And up until that point, no one had really studied how sand, it was actually what they flew was a sand column, and they flew it vacuum packed, brought it to orbit, released the vacuum, and then sheared, they pressed this sand column together, and they were watching the shear dynamics of this soil sample. It had never been done without gravity. It's really weird. But we live in gravity. It's pervasive. We can't do anything about it. We're here. What can you do without gravity? That's really a good way to look at how to figure out science for this. Metal solidification and alloys. Well, a lot of folks are like, how in the world can, with 2 watts of power, how can I melt a metal and resolidify it? You can. It's called a fuse. Or any other, there are very, very many other ways to, say, melt the metal. You can store up your energy for a while in a capacitor, or maybe some sort of a battery mode, although we'll talk about batteries in a few minutes. But there are ways we could store energy and then create a small furnace with small, small particles, small samples that we could melt and then re-solidify. It doesn't have to be metal. It could be any kind of compound, and just see how it operates in a microgravity situation. Also, there's in the past I've flown zone furnaces where you have like a solid sample that's in a rod shape, and you have a heating element that translates across the shape, and it only melts a certain section of that sample as it goes along. So it's called zone solidification. And that's another very useful technique, and it concentrates the energy onto the sample, but it uses a small amount of electricity and power. Vapor liquid phase experiments, this is kind of related to the fluid side, but there's also another big problem in microgravity, or it could be a big solution, where you have vapor and liquid phase experiment problems. Liquids behave, they want to tend to go into spheres in microgravity, and you typically can have vapor and liquid phase transport going on that starts to get very complicated. There's a lot of potential in that area to solve a lot of problems using capillary forces or artificial gravity forces, many ways to handle fluids, pressure, using, say, semi-permeable membranes, things like this to control the vapor and liquid interface. Combustion science. Well, oh my gosh, I'm going to burn something in space. Well, it's possible. You can burn a little piece of filter paper in there. I know the safety guys are going to kill me, but I usually get in trouble with them anyway, so that's all right. We'll take the heat for that. That actually is a huge area that Glenn has done a lot of research in, and they've flown many very large experiments, and I think now it's possible to get it, you can get it small. We can get it into the box. Life sciences, of course. What do you want to do here? There's just, biology is infinite. The permutations, the combinations. I'll kind of go down the sub-list here. Plant growth. How many plants have grown in microgravity right now? And I can tell you, without knowing the actual number, I can tell you it is so small compared to the number of plants that exist on the Earth. We just haven't had the time. Like I said, in the past, we're flying on the shuttle, we had 2 weeks to grow something. That's like just germinating stuff. It takes time. We now have time. We can grow plants on orbit for a long time. In fact, we kind of have to be careful, because if you start growing plants in the cube, what will happen is it'll bust out of the cube if you give it enough food and resources. So you have to consider that if you're going to do any kind of botany experiment. You have to consider, or even any biology experiment, you have to consider you have a limited amount of resources, and you don't want your system to outgrow its home, especially on orbit. Microbiology, infinite combinations that are available, infinite ways to deal with this. We've flown some experiments where we basically have like a little bag of nutrient media that squirts into another bag that has bacteria in stasis. That's another thing too. Let's talk a little bit about keeping your experiments in stasis prior to operation. If you can design an experiment that keeps your live organism in some form of a stasis mode, that's very helpful, because, for instance, I like to use the sea monkey example, brine shrimp. Brine shrimp will stay in stasis for years. They're basically dehydrated. They go into this dormant state. There are many spores will do this too. Many bacteria will go into like a spore mode and just stay in this dormant state for years, and it's essentially a dry state. Get on orbit, shoot some water in, bam, they're alive, and they're alive on orbit. And now all of a sudden they're starting to reproduce on orbit and having generations of organisms that are reproducing in microgravity. You might have 10, 20, 30 generations, depending on how long you can run your experiment for, of microgravity, full microgravity life cycles. You may start to see some gene expression happening over that time. So you can do some incredible research in the box using these techniques. Small animal insect research. Jamie is in the audience out here. She flew these little squid. What kind of squid were they?
They're called bobtail squid.
Bobtail squid. They're really cool. They're about that big, and they lived in this little tube. And what is it? Yeah, not naturally, but they survived. And their life cycle is what, about 6 months? So they have a 6-month life cycle. And the way this organism works, it actually is, it's born, it's young, grows up, it gets old, they get cataracts, they get old age results at the end of 6 months. So you can see a full lifespan of an organism in 6 months. And you can take advantage of that. Jamie was injecting some bacteria, I believe, into the squid on orbit to see how they would react in microgravity to this exposure. So if you pick your organism and its life cycle to match what you're flying, or your time frame, say a 30-day time frame, you can do some really incredible science over that little bit of exposure. Crystal growth. So protein crystal growth, inorganic crystal growth, infinite palette of work that we can do here. Okay. Once again, the ability to see 30 days of microgravity for very slow crystal growth. You can do this using diffusion methods, using vapor diffusion methods, liquid to liquid diffusion methods, electroplating, like I said, electrowinning. You can grow crystals in this fashion. Many of these areas have not even been touched yet. Just untouched because it just haven't had the time and the availability to do this in microgravity. So you can do some really earth-shattering science here. I'd like to see some really cool white papers come out of this stuff, because you can do some amazing things that nobody's touched. Even I saw, I think it was on 134, 135 experiments, there was some electroless plating that was done. And they actually saw some crystal morphology changes due to microgravity from that. So some really cool stuff you can do there. Wide open field, infinite number of unknowns right now. Astronaut tools. Okay, well, this is something where I have a little bit of a human factors background in the astronaut area, the space program. The total amount of human time on orbit has been very small. If you really start looking at, like, everybody talks about how big the space station is. Well, the space station inside is as big as a 5 or 6 bedroom house. Okay. Most of you probably live in a 5 or 6 bedroom house. And I'm sure you'll find that your house is too small at times, with maybe 2 parents and 2 kids, right? Can you imagine 6 people living in something like this? And you don't get to go outside very often. You can't open the windows. Okay? So in the area of astronaut tools and utilization, anything that can help the crew do certain things, or even just basic living accommodations. In fact, I think it was Don Pettit, he came up with a microgravity coffee cup. This has been a problem. I used to work with the food lab at JSC. And how do you drink coffee in space? Now, when you drink coffee on Earth, it's hot, and you can kind of sip it, and you're sort of pulling it in using air suction into your mouth. And while you're doing that, you're cooling it. Well, on orbit, they drink through a straw. Have you ever tried to drink coffee through a straw? It ain't fun. And you usually you burn your tongue. So what Don came up with was this kind of a wavy plate kind of thing where you sort of squirt the coffee into the plate, and it's held in place by capillary forces, and then you can kind of sip the coffee from this. Actually, it's kind of like a bag, but does a double function of cooling the coffee, and then you can drink it. So, who would have thought? It's just, and that's another thing too, is if we do get into this area, we could probably arrange some time to maybe get some astronaut time to consult with some astronauts to see just what is it on orbit that we would like to see better. And this may be this is kind of a weird area. It's probably not in the solicitation, but it's something else I personally would like to see some people do some work in. And then just any other kind of low gravity research. I have a pet project that I'd really like to see somebody fly. I saw this some time ago, where someone had proposed creating a liquid mirror that used a combination. Well, some of you may know that you've seen liquid mirrors on the Earth where they actually have like a big telescope mirror. They pour mercury, and don't fly mercury, by the way. We won't do that. But they pour mercury into a large flat dish, and you rotate that dish. This is actually an old fluid mechanics question on tests. What shape is formed when you rotate this liquid mirror? Well, it's a perfect parabola. And that's because of the combination of gravity forces and centripetal forces are pulling this liquid out. And it forms this beautiful parabola. And you can make some giant telescopes on the Earth using this method. The only problem is they only point in one direction, zenith, straight up. So you're at the mercy of the Earth's rotation to see your field of view. In orbit, though, we have something different. We don't have the gravity vector. But what we do have to replace the gravity vector is capillary forces, or surface tension, actually, of the liquid surface. So what I'd like to see is somebody fly a little spinning plate with a liquid in it, and then it uses surface tension and centripetal force to try and create this parabola. It's been hypothesized that this is possible. Nobody's ever tried it. So, make me happy. Space environment. Okay, so now that we've gotten past microgravity, and of course, once again, I'm sure there are a lot more smarter people around here that could add a lot more to this list. There are many, many things that we could do with just the microgravity component. On the space environment side, in low Earth orbit, where we're at, we are actually below the Van Allen belt. So the radiation environment is not as, say, evil as it could be, say, outside of the Van Allen belts, or particularly inside the Van Allen belts. It's a very, very high radiation field. But it is unique, and it is also, what I understand from researchers, they can extrapolate the radiation dosage from the low Earth orbit to, say, outside of Earth orbit situation, or interstellar space situation. So, and we do see regularly, laptops on orbit do see what are called single event upsets, which are induced by radiation hits onto the laptop computers. So we see this. And this is something, too, you may want to consider, although we have pretty good protection in the NanoRacks. The NanoLab cubes themselves are fairly well protected because you've got the aluminum from the space station, plus the aluminum of the locker and surrounding hardware, and also the aluminum of the cube itself. But for those who are interested in radiation exposure, we can, of course, minimize some of the metal path in between there and get some better exposure. It's also possible to store some of this stuff outside of the NanoRacks lockers, maybe near a window or something, so we get better radiation exposure. The radiation environment, as I said, it's not as harsh as it would be in the interstellar space situation, but we definitely do see increased radiation at this altitude. Radio frequency studies. This is another area. It may not be really applicable in this case, but it is possible, though, to pick up, say, high frequency HF band radiation. Of course, we There's a lot of ham amateur radio work that's being done. In fact, the CubeSats themselves typically use ham radio transceivers to communicate with the ground. One area that I have been particularly interested in is ionosphere propagation, or maybe even extremely low frequency radio wave propagation in space, and methods of detecting ELF in space is very important for a variety of uses. Magnetic fields, of course we have full exposure to the Earth's magnetic field in the space station. And we haven't flown it yet, but we could fly magnetometers inside the space station. They'll be fairly, it's in a fairly benign magnetic environment, and observation and mapping of the Earth's magnetic field is definitely possible with an interior experiment. Spacecraft hardware qualification, this is something where this is a little bit more on the engineering side, but for those of us who are in the industry, you do have a problem with technology readiness level. TRL 7, which is right in the middle of the, well, it's towards the higher end of the scale. TRL 7 basically says, look, you have to fly something in space before you can say it's actually space qualified. It's like, oh, okay. And this always forms a dilemma, or a kind of a paradox for flight hardware manufacturers, because what you'll see is, say I want to fly a brand new computer on a communication satellite. Okay, that's a great idea. It's a very powerful computer, it can do all this extra work, etc. But the insurance company will come in to the satellite manufacturer and say, oh, well, are you sure that'll work in space? I don't know. I've never flown it in space. So this is why a lot of space hardware uses old computers, old stuff, because, oh, I flew that before, I know that it works, I can use it on this satellite, and my insurance company is going to pay for insurance to cover the, the potential cost of a failure of the spacecraft. So a lot of risk aversion. NanoRacks, I have a little motto at NanoRacks I like to use. I say, we're cheap enough to fail. Okay? And that, from the laughter, you know what I'm talking about. And also we have the frequency where you can fail too. We can fly, at least every quarter, maybe 8 times a year. If you fail here, okay, wait a couple more flights, send you back up, fix the problem. This is particularly important for advancement of aerospace grade technology in the future. And I think this is going to be a critical element of really the space station, is providing this type of utilization and capability that's never been provided before. So, component testing, system testing. This may even go to space mechanics, where you see deployable mechanisms. We can take things out into the aisle of inside the space station, play with say a solar array deployment system, maybe a new type of robotic arm or something like this. That, ideally for this solicitation, it folds up and fits into a box. Take the box out, all of a sudden you start deploying a solar array. Wow! And I can see its dynamics and microgravity. Is this thing, what is it doing? How is it behaving? Very powerful information. Okay, so getting on kind of the implementation side of this chart. I say keep the mass low, but keep it around a kilogram. If it's a little bit over a kilo per U, that's okay. It's not a big problem. The box, of course, we have aluminum polycarbonate box. If you want to make your own box, that's possible too. You need to make your own enclosure. You don't have to stay inside this box. You can make your own box if it's more useful to you. Of course, we want to keep the power low, and we can use the crew to do things. So a lot of cases, if you need to lean on the crew, or if it's a crew interaction type of payload, that's okay. I always stress, though, that if you do have something that's very time critical, you're probably going to want to automate this before pushing it onto the crew, just because the crew is rather busy right now. So USB devices. I have a funny story of this. I don't know if people in here are aware of Fry's Electronics. I'm going to promote Fry's. Fry's is a local outfit in Houston. Well, it's a chain, but they have stores in Houston. I think they started out of California, if I'm not mistaken. But Fry's just has everything electronic. I love this place. It's a geek's paradise. Okay. So I took my son, who is not a geek. He's a business major. He fell far from my tree, right? And I said, my son was, I think, about 19 at the time, and I said, Brandon, I want to go into this store and find a cool USB device that we can fly on the International Space Station that would be useful on the space station. Now bear in mind, USB devices, there are approximately 6 billion USB devices in use right now, which is phenomenal. I mean, if you start adding up how fast these things have been made over time, USB 2.0 has been in existence, I don't know, Steve, for 10 years maybe? Something like that. So in 10 years, we've generated 6 billion devices. Everybody in this room probably has a USB device in their pocket, whether it's a memory stick or a cell phone, something in your car that works off of USB. So we walked into Fry's, started walking around. It took about 15 minutes. And my son found a USB microscope. I said, wow, this is great. This would be really cool. Surely there's a microscope down on the space station. And we started looking into it, and it's like, well, there really isn't one up there yet. So actually, though, by the time we flew our USB microscope, we have 2 up there now. Normal transmission where you use microscope slides, and then we also have a reflective microscope, so it's like a little macro camera. But up until that point, there really was only about 1, maybe 2 microscopes on board, and they're very complicated. They're really more like glove boxes that take quite a few hours to operate. Whereas our microscope, we pull it out, the crew plugs it in to the USB port on the laptop, and it's ready to go. It takes about 5 minutes to set up. So in your experimental work, in the event that you may want to use some support equipment like that, we have two microscopes on board that you could use as support hardware to take microscopic video or maybe even kind of macroscopic video of your science. So that's possible. So as far as sensors go, well, okay, getting back to USB devices real quick. The microcontroller is my favorite. This is the Maytag timer, but it's programmable. It's really just a miniature computer at your disposal, and you can do anything you want with that. You can drive electric motors. You can, read sensor information, take camera data. Just infinite combination of things you can do with this. So, sensor, on the sensor side, camera. There's tons of cameras. Steve's got a favorite, I think, that works very well, a USB type camera. It's the size of a dime. Okay, it's incredible. This was not available 10 years ago. And they're getting smaller by the moment. Your cell phone, you probably have 3 cameras in your cell phone right now. If you've got an iPhone, or maybe 2. It's just amazing. Spectrophotometer, along similar lines, the manufacturers are making miniature spectrophotometers that will interface with these boards readily. You can take chemical measurements and whatnot with these. A microphone. This one is a favorite of mine. Back in the early days of the space program, they would fly microphones with membranes on satellites to detect micrometeorites. It's a very robust and useful device. Accelerometers, of course, with MEMS accelerometers. The accelerometer is less than 1/10 the size of my pinky fingernail, and it measures accurately in all 3 axes. So we can detect, for instance, we can detect when we're in microgravity, and we can also detect microgravity disturbances, or if you have an accelerometer, say in a centrifuge, something that's rotating, you can measure your actual G-forces, Coriolis forces, etc. We can fly in MEMS gyroscopes. In fact, Steve's board has an accelerometer package on it. Is that a gyroscope too? I'm sorry, gyroscope too. So you get that with the board. Temperature sensor. You have a temperature sensor on the board, right? Humidity sensor. I know you don't have that, but that's not on board, but it's about the size of a match head. For those of us who know what a match is, right? Airflow sensor. There are many ways you can do this. There are cooling type of sensors or anemometer sensors. Pressure sensor. You don't have that on the board, right? No, okay. But that could be mounted on the board. It's also another small chip where it'll measure absolute pressure. Basically has a vacuum chamber on one side of the pressure sensor and then measures the delta P. Capacitance sensors, of course, a plethora of things you can do with this. Microphones, distance measurement, lots of stuff. RF sensor, it's also kind of a neat way to detect your environment. Just plethora. Resistance, magnetic sensors. Hall effect sensors, another excellent way to sense proximity or rotation of components. You see Hall effect sensors, say, in your car engine. They're very robust, measuring the rotation of a shaft or something. On the actuator side, of course, we can have the old traditional magnetic motor, solenoids, piezoelectric actuators are very, very popular nowadays. Very small. I've seen some fascinating ultrasonic linear motors that will move, say, in a straight line and stop and hold. A pico motor. It's made by New Optical. Fascinating device. It rotates a shaft. The shaft locks. As soon as you remove power from the actuator, the shaft is locked in place. It will not move. It's a good time to be alive. There's a lot of good stuff you can use out there. Thermal actuators, the bimetal or shape memory alloys are popular actuators in this area. Capacitive actuator with the MEMS devices. You know, in the past, capacitive actuators were typically relegated to the use of high-frequency speakers or something like this, where you had very close proximity of a membrane to membrane. But now with MEMS devices, you see capacitive actuators operating very tiny machines. And in fact, too, MEMS is a whole area that I think has been sorely neglected for use in space applications. If I could see some MEMS proposals coming in too, I'd be very excited. It'd be really neat. Of course, speakers, LEDs, LCDs, these are popular. Flag indicators, in some instances, we can use these as they're kind of old-fashioned, but maybe useful in some instances. Galvanometer, various valves, Lee valves, we've flown these quite a bit. They're tiny, tiny valves and pumps that can do some fantastic microfluidic work. Of course, the heater is very simple, and Peltier cooler. One of the other USB devices that my son found was a small refrigerator that plugged into your laptop to keep a can of Coke cold. That was a little extreme, but it's possible to put a Peltier cooler inside here and run it off with a 2-watt feed. So here's some past, a couple of examples. I put this together kind of quickly. I've got some even better examples of smaller experiments, but this experiment here was flown by Valley Christian. These are high school students that put this together. It was a 2U box, it had a plant growth chamber in it with LED lighting, its own camera. It had a water supply with a Lee valve that would supply water and nutrients to the plants. It had a humidity temperature sensor, data recording system, and this flew on just flew on HTV-2 and was returned on the 24 Soyuz flight. So this is a fascinating experiment, all in the box. Mixed sticks, this is an example of some, we've flown these about 6 times now, where it's just a very simple experiment where we have 2 fluids mixing together in an enclosed container. A lot of things we've done there is crystal growth, biological experiments, various chemical experiments. So, getting on with the design process, you know, what we'd recommend is that you show us your payload design. Of course, this will happen in the vetting of the Space Florida solicitation. You go back, and once you're selected, you make your final design modifications. We'll send this through the NASA safety review and verification activities. NanoRacks will take care of all this for you, so you don't have to worry about well, the only headache that you'll have is us bothering you for information. I call it the data monster. We need data. We'll need to know, like, your materials, your chemicals, what you plan to do with it, how you want to use it, and then we'll handle all the rest of that on the NASA side. Step 7, NanoRacks flies and helps you operate your payload. We have a mission control center in Houston that we operate through the Marshall Space Flight Center Payload Operations Control Center, and we will hook you in via internet, email, however, whatever system you'd want to use. We'll hook you into our control center to operate your payload. You'll either get your data back from on orbit, we'll downlink it and ship it directly to you in a secure fashion, or you'll get your, or you'll get your payload back from space. In the case of the Valley Christian payload, we flew it up in space, we were downlinking data, and we returned the payload to the customer. And then step 9, we encourage you to repeat. We like that part. So, conclusion, over the next month, design your NanoLab payload. Sign up for the Space Florida solicitation. Let's get your payload flown. And then we also like to see it published too. That's really cool. We'd really like to see that. And here you see Shannon Walker. She's installing our first NanoRacks frame on orbit. So yes, it is on orbit, believe it or not, it's there. And you can visit us at nanoracks.com. And once again, thank you, Space Florida, and for your excellent support here. I'm really looking forward to a fantastic program. And I'll take any questions you might have. Yes, sir. Yes. Steve will be talking about that this afternoon. So he's got a really nice set coming for the microcontroller system.
Mike, if you get some questions, could you repeat the questions in case
sure.
the live stream people don't hear the questions?
Absolutely. Yeah, the question was, is there a developer's kit for the microcontroller board? And Steve Bress will be talking about that later this afternoon in detail. Yes, there is. Yes, sir. Yes, okay. The question was, we have a lot of capability of monitoring and observing temperature, humidity, pressure, etc. Do we have the capability of controlling such situations? And the answer is we don't have that directly, okay? But within the confines of your experiment, you can design that. For instance, you may have an enclosed chamber where you could change the pressure. You might have a little vacuum pump on the outside and draw down the pressure. You can control a temperature by putting a heater in, say, and controlling that heater via your microcontroller board. Relative humidity is a little more of a challenge controlling, but I think it's possible to do that through a variety of, say, desiccants and or salt solutions, humidity, etc. So, yeah, a little creativity goes a long ways in this area, definitely. Yes, sir.
Do you have like a questionnaire or something like that for a user that would be designing one of these, or especially in the safety area? You said you'd be going back asking a lot of data. If you have a good questionnaire to start with, that might solve some of it.
Well, okay, so the question was, do we have a questionnaire that users can fill out to supply data to NanoRacks to aid in the development process? To be honest with you, I don't have a formalized questionnaire. Usually what we do is we just interview the users, and I found that it's a much faster, more effective way to kind of core down to what folks are really after. So we at NanoRacks, we take a very personal approach. to flying these payloads. It takes a little more time, but I think it's a lot more effective in the give and take between the experimenter and the implementer, if you will, the NanoRacks. So, but I think, you know, even today, if you had questions today, we could definitely address these, and we can also take questions on our well, through the Space Florida solicitation, and also on our website too. We have some question input systems.
In the solicitation, I'm sorry, in the registration application, there are some questions in there that sort of lead you through it. The questions include what kind of environmental conditions do you require, what's needed to automate your experiment, those types of things. And those are in the hopes to get these kinds of questions, get these kind of answers from you.
Yep.
So when you submit your application, make sure to pay attention to those questions, because that's the purpose for this one.
Yeah. Yes, sir.
Do you have any idea what the thermal environment is? You're using the express-rack
Yes.
system.
Yes.
You got up to 2 watts for each of the things. What kind of temperature environment might you see?
Okay. The question was, what is the temperature environment, say, inside the NanoRacks locker? And typically what we found is about 80 F, 80 degrees Fahrenheit. And relative humidity, I think, is on the order of like 72%? I have to go back and check the relative humidity, but it's typically just ambient condition, except it's about 80 F. It's a little bit higher than, say, 68, 70 F room temperature. And this is primarily driven by the express rack itself. There's a plenum behind the locker mounting plane, and they have a heat exchanger back in there that controls the temperature of the air. And the relative humidity is basically maintained constant throughout the space station. So the ambient air typically is what we're getting in the back. There's a small temperature rise. We have a little bit of heat that's thrown off from the payloads and the power supply in the central box. But it's only about, it's like around 1 degree F. It's very small, and the air circulation is such that the delta T is very small. Yeah. Another question? Yes, yours.
A standard microfiber plate for your plate heater.
Yes.
Is actually about 12 3/4 centimeters by 8.5. So that doesn't really fit in a 10 by 10 cube. Does an expanded cube actually?
Yes. Yes.
Does it fall under this competition?
Yeah. The question is, would a standard microplate fit into a cube? And if I recall correctly, the answer is no. But with the extended plate or the extended cube, we can get those microplates to fit in. And I believe we'll go with the extended cube for the solicitation. That's really not a problem. The real problem is if we go larger than 1.5 U, we have to go in the other direction. Then it would overstep the bounds. But the 1.5 is applicable.
Time for one more question, I think, from Dan.
Yes, Dan.
Great. Well, Dan for Florida Tech, and before I answer the question, I just wanted to thank you for that presentation, and
Thank you.
also on behalf of my university and all of Florida universities, I just wanted to express thanks to Space Florida for having this day and this competition. It's just so inspirational to sit here. It's going to be great for the winter students of the state and around the world. So thank you again, Tony, for that. My question is, when I think about some of the challenges on this, I think about like EMC compatibility, vibration testing, outgassing.
Okay.
Those are things that have actually been tougher for me than my science payload
Yes.
in the past. Whose problem is all of that? Is that NanoRacks, or do I need to EMC qual outgas
Okay.
and do all these things, or did we find a way to subvert all of that?
So here's where your life gets exciting. NanoRacks takes care of all. Well, actually, the real question is: do we have to? Are the experimenters responsible for EMI?
All your qual.
Yeah, all the qualitative
Outgassing,
tests, outgassing, off-gassing, vibration. NanoRacks takes care of all that, and that's all included in this package deal. So we will ask you some questions about certain things. For instance, materials is a big thing.
Yeah.
We have to have an extensive materials list that we'll submit to NASA toxicologists. And that's always a pain. That's like pulling teeth. But if you get that to us in a timely fashion, we'll get that through the system, and that in turn will determine a lot of the levels of containment for your payload, et cetera. So but we take care of all that headache.
You're the interface for that all the time.
I have a lot of Advil. Okay, I'll take care of it for you. One more. Biocompatibility. The question was, is biocompatibility included in our tests? We don't care about biocompatibility. So in other words, if you're going to make an experiment that requires materials that are biocompatible with your experiment, that is your problem. Yeah.
Okay, Mike Johnson, that was absolutely
Thank you.
superb. Let's give Mike a really round of applause.
Thanks, Tony.
Thank you, Mike.
Appreciate it.
Wonderful. I know Mike will be available today for private consultations and all the NanoRacks personnel, and if you have questions and rules and regulations, we'll try and clarify them.